is Vodcast 7.2. Now that you know how to balance a chemical equation, we're going to look at what a chemical equation tells us. A balanced chemical equation is just like a recipe. A recipe tells you at least three things. It'll tell you the amount of reactants needed. If we're going to bake brownies and we use the box, we're going to cheat a little bit. On the back of the box, it'll tell you what else you need, what other ingredients or what other reactants you might need to bake your brownies. It may list an amount of water, an amount of oil. It'll tell you how many eggs you may need to bake your brownies. It'll also tell you the conditions for the reaction to occur. It may say that you have to bake it at 350 degrees, maybe for 20 minutes. The third thing it'll tell you is how many products you're going to produce. After that 20 minutes at baking at 350 degrees, you may get 24 brownies or so, depending on the size you cut them at. A balanced chemical equation will define the ratio of the reactants to the product. If you get 1 box of brownies, you'll get 2 dozen as your product. If you bake 2 boxes of brownies, you'll get 4 dozen brownies as your product. A balanced chemical equation can also define the energy involved in the reaction. It'll tell you how much is required, or if it's exothermic, it'll tell you how much is released. So let's look at an example. Here's my example equation. A balanced equation will show you proportions. Those are my coefficients. Here in this balanced equation, my coefficient is 1 to 6, yields 6 to 6. These relative amounts can be expressed as either molecules or moles. We're primarily going to be focused on the ratio as a mole ratio. Whenever we want to convert one substance to another, we have to get to moles, and then we're going to have to use these mole ratios. So 1 mole of glucose reacts with 6 moles of oxygen gas to form 6 moles of carbon dioxide and 6 moles of water vapor. As you can see on the bottom, these are all of the conversion factors that you can use, depending on which substance we're starting from and which substance we're going to. Again, we're going to be using our FLM, and things are going to cancel just as they did before. Now it's going to be very important for you to add your units on the end so that we can keep track of what substance we're actually working in. Here's a sample problem. Again, my same reaction. If I have 1 mole of sugar, which is glucose, I'm going to produce 6 moles of oxygen gas. Well, you can easily see that when I double that, if I have 2 sugars, I'm going to get 12 oxygens and 12 carbon dioxides and 12 waters. If I take that to 4.5, I just take 4.5 times my ratio of 1 to 6, and I get 27. Sometimes it won't be quite so easy. So here's an example. If I have 15.3 moles of glucose, how many moles of carbon dioxide will be produced? Well, again, you always start with what you're given. 15.3 moles of glucose, which is C6H12O6. If I have moles of glucose on top, guess what I have to put on the bottom? 1 mole of glucose, C6H12O6. Exactly like we did before. Now my conversion factor, I'm going from glucose to carbon dioxide. What's my ratio? 1 to 6. So 1 mole down here of carbon dioxide gives me 6 moles of CO2. Moles of glucose cancel, and my answer, if you multiply that out, 15.3 times 6 gives you 91.8 moles of CO2. We can look at another example. Same equation. If I start now with 150 grams of glucose, C6H12O6, starting here, I want to convert to energy. Now you can see in my equation, I've added some energy. My energy is a product, so it must be an exothermic reaction. So I'm going to need my conversion factor here. If there's no number, we're going to assume that it's a 1. What's my ratio from glucose to energy? How many kilojoules? 1 mole of glucose gives me 2,870 kilojoules of energy. Now, that's my mole ratio. So what do I have to do first? If I have 150 grams of glucose, first I need to convert to moles. Well, I just so happen to have the molar mass of glucose is equal to 180.18 grams per mole. So if I have grams up top, I need to put grams on the bottom. 180.18 grams of C6H12O6 is equal to 1 mole of C6H12O6. Grams cancel. I'm now in moles. I can now use my mole ratio of 1 to 2,870. So 1 mole of C6H12O6 equals 2,870 kilojoules of energy. Again, moles cancel with moles, so my answer is going to be in kilojoules. If you take that and multiply it out, 150 times 2,870 divided by 180.18, you get 2,314 kilojoules as your final answer. Another example with a different equation. First, what you're going to have to do is balance this equation. You can start your inventory just like we did before if you have to. Sometimes they're easy enough and we don't have to. In this case, if I have 8 sulfur on the left, I need 8 on the right. So if I put a 4 coefficient out front, that would give me 4 times 2 is 8. But that also gives me 4 times 2, 8 chlorines, which means I have to put a coefficient of 4 out in front of my chlorines. Now my ratio is going to be 1 to 4 to 4, and I should be balanced. So first we have to balance before we do any kind of conversion. Here's my first problem. How many moles of product, that's this guy, how many moles of product can be formed when 2.5 moles of S8 react? Start with what you're given. What am I given? 2.5 moles of S8. When you're in moles, you can use your conversion factor, which in this case is 1 to 4. 1 mole of S8 equals 4 moles of S2Cl2. Moles cancel with moles. 2.5 times 4, we can do this in our head, gives me 10 moles of S2Cl2. Okay, what if we add another step? What is the number of moles of product? I'm still trying to get the same thing. I'm still going for moles of product. Now I start with 825 grams of S8. Still starting with S8. Now I have grams. First I have to take grams to moles, and then I can look at my mole ratio. So I start with what I'm given. 825 grams of S8. Now what do I need down here? I need grams of S8. So I need the molar mass. Sulfur is 32.07 grams per mole. I have 8 of them. My molar mass is 256.56 grams per mole. 256.56 grams in 1 mole of S8. Grams cancel with grams. I'm now in moles. Now I can do my mole ratio, which is 1 to 4. 1 mole of S8 gives me 4 moles of S2Cl2. Moles of S8 cancel with moles of S8. If you multiply that out, 825 times 4 divided by 256.56 gives me 12.9 moles of S2Cl2. And the last example I have for you today has to do with this equation. Here it's already balanced for you. 1 to 6, yields 3 to 4. That's my mole ratio. But remember, if it's given in grams, you have to get from grams to moles first before you can use that mole ratio. So, first problem. How many moles of KOH was used? So I'm trying to get to KOH. If I start with 500 grams of K2SO4, always start with what you're given. 500 grams of K2SO4. If I have grams of K2SO4 up top, what do I need on the bottom? I need grams of K2SO4. K2SO4, molar mass, if you add it up, should equal 174.27 grams per mole. So, 174.27 grams of K2SO4 is in 1 mole of K2SO4. Grams cancel. Now I'm in moles. I can do my mole ratio. I'm going from K2SO4 back to KOH. So my ratio is 3 to 6. 3 moles of K2SO4 equals 6 moles of KOH. Moles of K2SO4 cancel. My units at the end are going to be moles of KOH. And if I multiply this out, 500 grams times 6, divide by 174.27, divided by 3, my final answer is 5.74 moles of KOH. And for the last example, how many molecules of FeOH3, that's this one, how many molecules of FeOH3 can be formed when 25 grams of KOH react? Where do I start? Start with what you're given. 25 grams of KOH. If I have 25 grams of KOH, before I use my mole ratio, I have to get from grams to mole. KOH, if you add up the molar mass, is equal to 56.11. Grams of KOH on the top, I have to cancel with grams of KOH on the bottom. There are 56.11 grams of KOH in 1 mole of KOH. Grams of KOH cancel. Now I'm in moles. Now what can I do? I can jump. Mole ratio, 6 to 2. There are 6 moles of KOH for 2 moles of FeOH3. Moles of KOH cancel. I'm now in moles of FeOH3, but my problem wanted to know how many molecules of FeOH3. Now we got to use Avogadro. 1 mole of FeOH3 always equals 6.022 times 10 to the 23rd molecules. Moles of FeOH3 cancel with moles of FeOH3, and my final answer is 8.9 times 10 to the 22nd molecules of FeOH3.